This video will look at the dependence of cell potential on concentration. Sounds like a good one, right? So we've always been talking about this cell potential, this force that pushes electrons through a system, and that we've had solutions that are 1 molar. Standard cell potential is measured with solutions at 1 molar. And people will always kind of ask, when you see this little degree symbol by your cell potential, like here, there's that little degree up there, it has nothing to do with temperature. It just means that the cell is under standard conditions. And you see that a lot with the thermo too, like delta G might have a little degree symbol, or delta S, delta H, and it just means that everything is at its standard state of matter, standard conditions. And with cells, or these electropotential cells, we assume that the solutions are 1 molar unless told otherwise. Now, they can obviously be otherwise. We don't have to run cells with 1 molar solutions. Enter in the Nernst equation. This is a good one. It looks pretty beefy, but there's a lot of good stuff that can come out of this equation. It's totally in your packet. It's plug and chug. They'll tell you what all the symbols represent. We just have to know when to use it and then maybe how to use it. So we use this Nernst equation when we want to compare the cell potential at standard conditions, which would be at 25 degrees Celsius and 1 molar solutions, to a cell that is running at non-standard conditions. Now that could be a different temperature, but more often it's going to be that the solutions are not 1 molar. And so here's what everything means. When you have E without the degree symbol, this would be my cell potential at non-standard conditions. Non-standard conditions. With the little degree symbol, this is the cell potential under standard conditions. Okay, now we've got all this other junk in here. Where are we even going to put this? N. N stands for the number of electrons transferred in the redox reaction. Number of electrons transferred. Or we might say moles of electrons. Oh, I might even add that. I'll say number of moles. Yeah! I like that even better. Number of moles of electrons transferred. Okay, so we're going to have to look at the redox reaction and figure out moles of electrons. That's fine. F is a constant. It's called Faraday's constant, and it is in your packet. Faraday's constant. Totally in your packet, you look it up. It's listed in your packet as 96,485 coulombs per mole of electrons transferred. Coulombs per mole. Now they also will kind of tell you that a volt is a joule per coulomb. So they'll give us this conversion of, or a comparison between volts and joules, which will kind of come up in a second. Okay, then on the top we've got R and T. R is going to be your gas constant. Let's see if we can squish it in there. R is that constant. We want the one that's the 8.314 joules per mole Kelvin. And so what will happen is that we're going to have joules on the top, and this coulomb is related to a joule, so that'll cancel. We're going to have moles on the top and moles on the bottom. And T is temperature in Kelvin. Kelvin temperature. So I've got a lot of the same units working throughout all these variables. Holy cow, that's a lot. And then finally, natural log of Q. He's back. equilibrium has never left. Q is the reaction quotient. No way. It's the reaction quotient. It's that whole products over reactants thing. Products over reactants. It looks just like K, where we're going to set up the concentration of our products over reactants. We're going to raise them to the coefficients in the balanced equation. It's just that K, the equilibrium constant, had to be calculated using equilibrium conditions, and Q, the reaction quotient, is calculated with the real conditions that you have, and it might not represent a system at equilibrium, which is totally fine. So this is going to end up being the concentrations of the solutions that we really have. It may not be 1 molar. That's a lot. But all of those variables are spelled out for you in the packet. We just have to know that this is how we use the Nernst equation when we have a cell that's operating under non-standard conditions. For example, okay, so here's everything that I need. E cell, the standard cell potential is 0.48 volts for the galvanic cell based on the reaction below. Now we're going to run this cell where the manganese concentration is 0.5 molar and the aluminum concentration is 1.5. Calculate the cell potential for this reaction at 25 degrees. And then can I just kind of qualitatively compare that to what I might expect if I were maybe using Le Chatelier's principle, which is more of a qualitative look at potential and Q versus K. Okay, so we got to plug all this stuff in. Here's what I got. E, my new cell potential under non-standard conditions, equals my standard cell potential, 0.8 volts. Volts is totally an acceptable unit, minus lots of stuff. Okay, so on the top I've got R, 8.314 joules per mole Kelvin. T is my temperature in Kelvin. So my 25 degrees Celsius will become 298 Kelvin, which, by the way, it's in the packet. It's on the very back side of the packet, up on the top, where they'll tell you the switch between Celsius and Kelvin. Take your Celsius temperature and add 273. You don't have to memorize that. Okay, so it's opposite RT all over N. N is number of moles of electrons transferred. Now, we could kind of pick this apart. And so obviously I'm going to have like my two half reactions. I would have the aluminum turning into the aluminum +3 ion, the magnesium, forming the magnesium solid. You could separate the half reactions and balance them if you would like to. Where if I do a little sidebar, I'd have the 2 aluminum, and they are forming the 2 aluminum +3 ions. The particles are balanced, but the charge is not. And the only way I can balance the charge is by adding electrons. Ah, okay. So I've got neutral on the reactant side. I've really got a +6 on the product side. As is, this would transfer 6 moles of electrons. Oh, yeah. And then it totally works out with the other half reaction. That if I had the 3 manganese +2 ion, they would need to gain 6 moles of electrons to form the 3 moles of solid manganese metal. Now maybe you could figure that out without separating the half reactions and balancing them with the charge. And if you can kind of figure that, oh yeah, there must have been 6 electrons balanced from the original balanced equation, game on, that's fine too. Often in a free response question, which obviously this Nernst equation has to be free response, but usually in like a previous part of the free response, they may have even asked you to balance the redox reaction, or maybe they would have asked you how many moles of electrons are transferred, so that if you balanced it wrong, or if you had the wrong moles of electrons transferred, but you used it in the Nernst equation properly, you wouldn't lose any further points here. But there are 6 moles of electrons transferred. And then F is my Faraday's constant right out of the packet. 96,485. In the packet, they'll use the units coulombs per mole of electrons. Oh my gosh, we barely have room for this thing. All of that times natural log of Q. Oh brother, we have to figure out Q. Okay, so Q looks just like K, the equilibrium constant, but it's with the conditions that we have. So we'll do a little sidebar, we'll plop it down here. Q equals products over reactants, but hey, it's not so bad to review some of this equilibrium stuff. Remember that when we set up equilibrium constants, we do not use pure liquids and solids. No liquids and solids in an equilibrium constant or in the reaction quotient Q. We only use solutions and gases. And eventually, when we set up ice tables like many moons ago, the only things that you could use in an ice table would have either been pressures or concentrations. So we are not going to use the solid manganese or the solid aluminum. Q will be the concentration of the aluminum ion. That I can use 1.5 molar aluminum plus 3. And then we raise that to the coefficient from the balanced equation. 2. Products over reactants. The 3 moles of manganese. And the manganese is now 0.5 molar. Manganese plus 2. And then the 3 becomes my exponent. Okay, so we plug all this in. 1.5 squared over 0.5 cubed. And Q is a big fat, interesting, 18. Then that goes up into my Nernst equation. Natural log of 18. That was Q. Holy cow, this is a lot. But now it's just all plug and chug. You just plug it in your calculator and let's see what we get. Okay, so 0.48 minus all of this. Wow. 8.314 times 298. I'm going to divide that by 6. And by 96,485. And then I'm going to multiply by the natural log of 18. Craziness. Okay, then we plug all this in our calculator and we see what we get with a reasonable amount of decimal spots and sig figs. So yeah, I mean, if the original cell potential was just 2 decimal spots or 2 sig figs, I think I'll do the same. My new cell potential is about 0.47. It's a lot of work for a number that didn't change by much, huh? So it went down ever so slightly. Okay, which is great. So this is all plug and chug. I find all the variables in my packet. I got to know how to get Q, the reaction quotient. That I got to do from back in my equilibrium days. But maybe more important, is this what we would expect based on Le Chatelier? Now, warning, on the AP test, they will not allow Le Chatelier as an explanation of whether or not this new cell potential is legit. which is really kind of disappointing. And I argued about that one time, and the grader just said, no, we will not allow students to explain the new cell potential versus the standard cell potential by talking about Le Chatelier. Oh, but your book does. But for some reason, the College Board will not accept that, and I'll just get over it. But let's look at this. Is it what we would expect? So Le Chatelier would say that if you add something, you shift away from what was added. So here we added extra aluminum. In a standard cell, it would be 1 molar, and now it's 1.5 molar. So yeah, if this concentration were higher, I would expect that we would shift away from what was added. I would expect this thing to shift in reverse. And if I'm shifting in reverse, then I'm going to decrease the cell potential. And that's the force that's pushing the electrons forward through the system. It's what's pushing and driving the reaction forward. And so if I do something to make this reaction go reverse, then yeah, that would decrease the cell potential. Now it also works if I look at the manganese, that here my manganese is decreased, and so if you reduce something, you want to shift in the direction that replaces it. A standard cell would have a 1 molar solution, so now this is less. Oh yeah, then I would be shifting in reverse. I'd want to replace the manganese. Now obviously these both point to the reaction shifting in reverse, which is why the cell potential drops a little bit. Now you could have one variable increase and another variable decrease, and then if you can't predict the change in cell potential qualitatively using Le Chatelier, you would just have to plug it into the Nernst equation. Now often on the AP test, if they want you to explain this change in cell potential, they would either give me something that's obviously like this, where it's pretty predictable, or here's what they want you to do. They want you to explain this by comparing Q standard to Q non-standard. What? Okay, so it's going to look like this. In a standard cell, Q standard it will always be 1. If this were a standard cell, then all solutions are 1 molar. So standard would have this as a 1 molar solution, and this would be a 1 molar solution. And so it doesn't matter what the exponents are. In a standard cell, Q is 1. Well, in a non-standard cell, Q will not be 1. So here, like my Q non-standard, oh yeah, Q is 18. Now, kind of reminds me back in the day when we were talking about Q versus K. Now, I'm not going to officially say K, the equilibrium constant, because we don't know that. We're calculating Q, which is just using the conditions that we have. But we don't have equilibrium constants here. But for any standard cell, Q is going to be 1. Now, if I compare Q standard to Q non-standard, when the non-standard is too big, and it reminds me of like the Q versus K thing. Oh my gosh, I'm running out of space. But if we're always thinking about Q as a ratio of product over reactant, if the non-standard cell is bigger than 1, then there's too much product. This is dominating. There's too much product, not enough reactant. We're shifting this thing in reverse. If it's going in reverse, the cell potential decreases. And that's how they're going to want you to explain this on the AP test. When they first have you calculate the new cell potential, okay, 0.47, and then they say explain it. don't say Le Chatelier, but instead we're going to compare our new Q under non-standard conditions to the value of standard Q, which is 1. So standard Q is always 1. And then we're going to say, ooh, under my new non-standard conditions, Q is bigger than 1. That means there's more product. I'm shifting in reverse. More product, or we could say less reactant, which is the case here too. Less reactant, well, I got to shift in reverse to make more reactant. But they want you to talk about Q, not Le Chatelier. And we got to compare our non-standard Q to standard, which is always going to be 1. So if my non-standard is greater than 1, then I either have too much product or not enough reactant, and it's going in reverse. If my non-standard Q is less than 1, then I want more product or less reactant. And if we do something that shifts this forward, then the new cell potential will increase. Then there's more force pushing the electrons through the system.